we apply a force to something, what changes? Newton's second law. Applying a force causes an acceleration, right? Well, applying a torque also causes an acceleration, but what type of acceleration does it cause?
Centripetal.
Not centripetal
Oh, no, it's
acceleration.
straight linear.
Yeah, the tangential acceleration, right? Because, remember, for centripetal acceleration, speed is constant. We are not gaining speed and slowing down. For tangential, if we are spinning and we want to figure out the tangential or the linear acceleration, then we are going to speed up or slow down, okay? So, torque causes an object to accelerate in that angular motion. The units are Newton meters, and the reason why is because what we're going to end up doing is we're going to take the force that we have times the radial distance from the pivot. All right, so force is in newtons and distance is in meters. So these are the units for torque. Okay, so torque is similar to force such that it causes an acceleration. It's going to be a tangential acceleration or alpha, like we can choose from the two. All right. The tendency of a force to rotate an object around a pivot is your torque. So it has to have some sort of axis for rotation. So if we're looking at a door, we have the hinge of the door. All right. Now we have 4 completely different forces, right? So the thing is, if you are going to rotate, how you rotate depends on the magnitude of the force. It depends on how far you are from the pivot, and it depends on the angle which the force is applied. Okay? So, when we look at this, we have torque is 2 equations. It's either R perpendicular to force, so your radial distance perpendicular to the force. This is your torque, or RF sine theta. This is really just the y component of your force, okay? So if you are applying a force at an angle to the radial distance from the pivot, what you're trying to turn isn't going to feel all the force. It's just going to feel part of it, the y component part, okay? The other portion of the force is the x component, which is not going to affect how much force is applied to the door to turn it. Okay, so when we look at this, we have our hinge, and we have this force right here, and it's moving in, force 2. Is this going to successfully open the door? No, we're pushing into the hinge. This is not going to move at all. One thing I also want to point out is if you're kind of looking at this like the x and y axis, right? Where this is 0. What is the angle measure here? 180. What's sine of 180? 0. So if we were to come back to this, right, RF sine theta, it would be the radial distance times the force, which maybe we are applying a force, but it's times the sine of theta. So your torque for force 2 would have to be 0. Now force 1 and force 2, how far are they away from our x-axis direction here? The angle. 90 degrees, right? So both of these are 90 degrees from the radius side. So the radius side is kind of like your x-axis, right? So what happens is this gives you the maximum amount of force on the door. But as we learned when we were doing the demonstrations, it's a lot harder to push the door when you're here versus when you're over here. So the way you're able to use torque to open a door, right, it is better for you to have a force further away because the amount of torque applied to the door is greater, which is why it makes it easier to open versus if you use the same amount of linear force at this radius. Does that make sense? So this is actually less torque, which is why it feels harder when you're applying a linear force. Good so far? When we push at an angle here, okay, what's happening is we are not getting all of this force in order to turn the door in this angular motion. We are only getting a portion of it, specifically the y component portion, right? So if I look at the 2 components here, so here's my force 3, right? Here's my y component, and here's my x component. Now, what degree does my x component make with the radial line? What's the angle of the x component here?
0.
For this one, it would be 0 because it's pointed to the right, right? So, but then the sign of 0 is 0. So this x component, well, you know, we're brushing up on that. So the x component of the force turns the door how much? If it's RF sine 0, how much torque is applied by the x component? 0, because the radius times the force times the sine of 0 would be 0. So the torque applied to help the door turn is 0 because the force is at 0 degrees with this radial distance. Now the y component, right, which is just going to be F times the sine of this angle theta here, this is what is actually helping our door to turn. So if I'm trying to turn my door in this circle here, right, I'm looking at only the y component that it is going to be applied to our torque. So this F sine theta, it's really because it's the y component, because the x component of your force when it's at an angle is not going to help to actually turn the door, because it is the force that is along the radial side. All right, so there's two things, method 1, method 2, of looking at torque when you have a diagram and trying to figure it out. I will say I personally prefer method 1, but I do want to show you method 2 because it's always valuable to see different ways to do things. All right, so we have, in this diagram, it's hard to see, but we have this force right here. Okay, this is our force. This is the perpendicular force. Okay, and this, it says like F1. This is like our x component force, or I guess you could say it's the parallel force. It's parallel to the radius. Let's go ahead and put parallel there. Okay, so here's the thing. This is my x component. This is Fx, and this is Fy. That's the component of this force. Is everybody okay with that? So here's my y component, and it's just slid over at the location of this force. Everybody good? So if that's the case, then, if I'm trying to figure out what part of the force is helping to turn this, it's always the perpendicular part of the force, which is really just the y component. Well, if I treat this like an xy axis here, okay, then this force is phi away from the radial line. So the x-axis line, right, is the radial line. Now the radius is only from here to here. It's from the pivot to the actual placement of the force. So if you're making this line, you're really looking at the angle that this force makes with this line. So to get the perpendicular force, it's always going to be F sine of the angle made with this line. Now the torque doesn't just depend on force though. What two things do you need for torque to make it move angularly? You need force and the radial distance, right? So that's this guy. So once you can identify this F sine phi, then you multiply it by the radius. That's going to give you how much torque that the door feels to allow it to turn in the circle. Good so far? Now we come over here. The way that this is different, right? Because here I'm really looking at my radial line, okay? Over here, we're looking at it differently because what we're doing here is looking at the force, the direction of force. So if I extend my force line instead, okay? So I'm extending the force line, and then I look to my pivot, and I'm going to draw from the pivot a perpendicular line, so an altitude to my extended force line. So that comes over here. Okay, and what this does, it creates a new side, and we're going to call that side R perpendicular. Good so far? Okay, so it turns out if I have the size of my force vector here, and I can get the side of this R perpendicular, right, then I can calculate the torque. Okay, now if you'll notice, right, if this is phi, right here, so the same, we have the same problem here and here. If this is phi, What kind of angle is that? What do we call this? Starts with a V. Geometry. Vertical angles. This is also phi. Good so far? So what side is this from theta? It's the we have a right triangle. If this is phi, what is our perpendicular? That side is the opposite side. I know, right? So therefore, what trig function do we need to use? If we were trying to calculate our perpendicular, you would still have to use sine to figure out that side. I do not prefer this method. The idea is they're actually exactly the same, but here you're taking f times r sine theta. Here you're taking r times f sine theta. It works the same way. One has to be perpendicular to the other. Not as straightforward, but you know, to each their own, right? Okay, so I think here there must just be directions here. So draw a radial line from the pivot through the point which the force is applied. So here's my x-axis line. The angle is measured from this radial line to the force. Or you can draw a line of action through the force. They're going to draw a line from this pivot to make it perpendicular. Okay, everybody good? All right. Next, this one. I do want to take some time to go over this because it seems pretty straightforward, but I'm finding as I teach this year after year that a lot of people are having problems with the direction of the torque, whether it should be negative, whether it should be positive. So I'm going to go over two ways to tell, all right? The first way to tell if your direction is positive or negative is identify the pivot point. So here's my pivot point, and you're going to put a pen or a pencil at the pivot point. You're going to hold it at the pivot point, okay? Now, do you see how this is a force right here? If I want to know if this force makes my line here move counterclockwise or clockwise, all I'm going to do is I'm going to apply a force in that direction. If I do this, which way am I spinning? Counterclockwise, which is considered the positive direction, right? So this force right here, is this going to make it go clockwise or counterclockwise? Counterclockwise. Everybody good? Yeah. Okay. How about this force? Clockwise. Right, we go this way. It's going to make it move clockwise. This guy? Clockwise. What about these two? Zero. Zero. It's not going to make it move at all. Okay, so this does not apply a torque because you're either pushing into the hinge or out, right? So that's not going to help rotate it so that it moves angularly. All right, is everybody okay with this? Of these forces, which is going to help apply the maximum torque? The perpendicular forces will help to apply. So the further you are from the radial distance, and if the force you're applying is perpendicular to the radial line, that's going to give you the largest torque, and it's going to make it easier then for an object to move angularly. All right, next page. All right, if I have a situation where I have multiple forces working on an object, what do I do?
One more time.
So I have multiple forces working on objects. I've got friction and applied force, and what do we do? We find the net force. Excellent. How do we find the net force? All we do is add them up. Right. We're going to add up all the forces. Well, torque works the same way, right? If you want the net torque working to make something turn, you just have to add up all the torques working on your object, okay?